Before we work out some of these gas law problems in more detail, I would like to take a minute just to mention, really to give you a feel for why we are covering a few topics from chapter 12 this early in the semester. And really it's because gas laws are fairly intuitive. It relates to things we can see and feel or experience with inflating balloons, temperature pressure relationships, pressure volume relationships. These all are fairly intuitive. And so we can relate the equations to something we can see, commonly in everyday life. So it gives you a better physical feel for the problems that we're dealing with. And also these problems really are very good practice for basic problem solving skills and for your algebra skills. And it really focuses on dimensional analysis, keeping track of the dimensions. The equations we're using here, I'll stress again later, I'm not going to make you memorize them. I just want you to know how to use them, how to apply them, and you should be able to understand the concepts. And really, if you keep track of your algebra, are very careful with algebra, and keep track of the units, make sure the units work out to give the proper units of the answers, then they're really straightforward and really gives you a good foundation for the rest of the semester. So let's look at this first problem. If a gas at 100 degrees centigrade and 760 degrees Kelvin occupies 1 liter, what volume will the gas occupy if the temperature is doubled and the pressure halved? So here, the first part of a problem-solving approach is deciding, really what do we need to do. If you can't see immediately what equation to use here, look at the gas law equations we have. We've gone through so far this, just 3 basic equations. One is let me write them out here. If I can get my pen to work. Sorry. One is just the P1 V1 over T1 equals P2 V2 over T2. Now what I'm showing you here is what I might do on the test, or I have done on tests and exams and quizzes before, where I may not at first see what to do. So I'll write down what I know. So in this case, I'll write down the equations we know dealing with gas laws. This says it's a gas, so if I can't see what to do, I'll look at the various equations. And so one of the other equations we looked at is PV equals nRT. And the last equation we've looked at is P total equals P1 plus P2 plus all the other partial gases that are present. And so look at these gases, look at these equations and the problem, and decide which equation best fits the problem. In most cases, this can let you know which equation do we need to use. So here, the first equation deals with changes in pressure, volume, temperature. And so, well, if a gas occupies gas 100 degrees C, what volume will the gas occupy if the temperature is doubled, pressure halved? We're changing conditions. And so this first equation is the only one that deals with changing conditions. So that's likely what we're going to use. We look at the other 2 equations. The second equation, PV equals nRT, well, we have constant conditions here, and it's dealing with a certain amount of gas particles, a certain amount of moles of gas. This problem doesn't discuss moles at all, so this equation is out. The last equation talks about combining several gases together. This problem doesn't even mention, different gases, so it's just a gas. So that can apply. And so this is one approach you can take. It's fairly simple here in this problem, but if you can't see how to solve a problem, this is part of what you can do to try to analyze a problem. And that's what I do quite, commonly have done in the past where I can't see what to do. Put down what you do know. All right, so let me erase all of these. Okay, there we go. And so what I often do, and I really suggest to, if you're not sure what to do, and with a lot of word problems, people have trouble with problems that are in paragraph form. Sometimes people can get tripped up. So I might put out, I might just take out of the, doesn't look very good there, but initial conditions and final conditions. I might just write out, take out of the paragraph what my information is, and that often helps us put the right numbers in the right places. So initially, we know our initial gas is at 100 degrees C. It's at 760 torr and 1.00 liters. Actually, 760 should be 2 sig figs, but anyway. Final temperature Temperature is doubled, so it's 2 times our initial temperature, just say T1 for, which of course will be 2 times. Now here you've got to be careful. When we talk about temperature with gas salts, we really need to have the temperature in absolute value, in an absolute temperature scale, in Kelvin scale. And so you need to know, in this case, you can look up the relationships. The degrees Kelvin equals degrees C plus 273. Therefore, this 100 degrees centigrade is going to be, actually, I'll stop here for a second. I meant to point this out earlier in the in this semester with these video problems. Whenever I present a problem like this and I'm going to work it out, a really good idea for you to do is to not watch the video and then watch me work it out. It's good to at least attempt to do it yourself first. Look at the problem, try to solve it, then I'll start working it out one step at a time. That way it helps you develop your skills better rather than just watching me do it. Because again, with this problem, there are several ways it can be approached, several ways you can do the problem. One way isn't necessarily correct, so I don't want you to try to memorize a solution, because the same information can be presented in lots of different ways. That can trip you up if you try just to memorize a solution. So in this case, my point here is we're given degrees centigrade, we've got to go to degrees Kelvin. So first, convert degrees centigrade to Kelvin. So here, I'll just give you the answer here. 100 degrees centigrade is going to be 373 Kelvin. And you can work that out for yourself for practice to make sure. And therefore, 2 times T1 needs to be 2 times our absolute temperature, or 2 times 373 Kelvin, which of course gives us 746 Kelvin. And I think, looking at this graph, I think you can't see the end of that equation. Sorry about that. I'll stick it up here again though. Degrees Kelvin is going to be degrees centigrade plus 273. So that's the equation you should use, look up in the book. It's fairly common knowledge, it's really good to know. And says the pressure is halved. So our final pressure is going to be 1/2 of our initial pressure. Just call it T1. I'm sorry, P1. Sorry. So half of 760 is going to be 380 torr. And our final volume, we don't know. That's what we're trying to find. And so now we have our numbers written out outside of the paragraph. And this helps the way many information can be given. People often mix up initial final conditions. This way you can make sure that you keep your initial conditions together, final conditions together, and plug them in the right areas, right places on the equation. So the P1 V1 over T1 equation, our initial pressure is 760 torr. And I recommend writing in units also. P1 V1 is 1.00 liters. Over T1 is going to be 373 Kelvin. Equals P2, our final pressure, we figured out is, oh, sorry, not pressure. Our final pressure is going to be 380 torr. V2, our final volume, we don't know. We're trying to figure that out. And over T2, our final temperature, is just going to be 746 Kelvin. And now we just solve for V2. All right, so now I'm going to just rearrange for V2. And this is a place where I suggest, or a couple things to suggest. One is that you keep track of units. It's easy to misplace values in the wrong area. If your units are in the right place, you can make sure they cancel out. So let me do this first before I do anything. Torr will cancel out torr. Kelvin will cancel out Kelvin. My only unit left is going to be liters on the left side, which is what I need. I can't cancel that out. My final answer should be in liters in volume. And then rearrange to solve for V2. And if your algebra is rusty, it might be a good time to pause the video and solve for V2 yourself. And should arrange to get 760 times 1.00 liters over 373 times, when I get V2 by itself, it's going to be 746 over 380. And when you work this out, you end up getting 4.0 to the proper sig figs, 4.0 liters. That should be the answer that you get. And at the end here, I always suggest try to do this yourself. It would have saved me lots of careless mistakes myself if I'd done this more often. Look at your answer and see if it makes sense. Do a sanity check. With gas laws, again, it's fairly intuitive. You have a given volume of gas, increased pressure, it gets larger. So here we've doubled the pressure. I'm sorry, we've doubled the, sorry, let me try that again. With a sample of gas, you increase the temperature due to kinetic energy, molecules move faster and faster. It expands. Higher temperature, a larger volume. We're increasing temperature, our volume should go up. With pressure, we're decreasing the pressure, and here the pressure is the pressure compressing on this, a balloon if you imagine. Decrease the pressure on this balloon, the balloon's going to expand. So in both cases, we're expecting the volume to go up by 2, so we get a factor of 4 change in volume, so it's what we expect. Both increasing temperature and decreasing pressure should increase the volume, so we get 4 times the volume. So that makes sense. It's a good way just to double check that our answer is along the lines of what we expect it to be. So let's look at another problem. So again, what is the volume of 2 moles of hydrogen at 100 degrees centigrade and 1.5 atmospheres? So now in this case, again, deciding which problem to use, which equation to use, I should say. We don't have any changing conditions. We have a volume, a pressure, a temperature, and an amount of gas molecules. We don't have a combination of gases, so the only equation here that makes sense, if you're not sure, look at this yourselves, pause the video, and see what you come up with, is to use PV equals nRT. Again, P is the pressure, V is the volume, N is the number of moles. And again, moles is just number. It's how many particles we have. We use moles again later in chemistry for chemical reactions. In gas phase, all that matters is how many gas particles you have. So a mole, 1 mole is just, as we mentioned earlier in the graphs, in the videos, it's just 6.022 times 10 to the 23rd. In this case, it's that many atoms or molecules. So it's just a number. So that's all we need to think of it as, is a number. R is a constant, ideal gas constant. And this we just look up in tables. In this case, is given for us. And T is just temperature. Again, temperature needs to be in Kelvin for all gas laws. If you're ever not sure what temperature should be, if it should be centigrade or Kelvin, convert to Kelvin. Kelvin's always one to work. So if in doubt, go to Kelvin. So this is our equation. So we just plug in variables and solve for the unknown. In this case, we're trying to solve for volume, but before rearranging it, I'll just put my numbers in. Pressure is 1.5 atmospheres. Volume we don't know, I'll leave the V here. N is number of moles. 2 moles. R we're given is 0.0821 liters atmospheres per mole Kelvin. And temperature is 100 degrees centigrade. Again, you should know how to do these conversions. At least how to use the equations from the text. And this will give you 373 Kelvin. And we just solve for our unknown. Now, one thing I want to point out is here where we're given an R, this value, pay attention to the units. That's a lot of the reason we're going through gas laws, is to get you paying attention to the units. The R has to match up the units of the other equations. You look in the text on one of the earlier view graphs on the PowerPoint, there are multiple values for R. They're all the same. It's just like talking about my height in feet versus inches versus meters. I have the same height, it's just different units. Same thing with R. There are different units even though it's the same constant. So you need to have the R that matches up with the units you're given so they cancel out. So before doing anything, let's make sure our units cancel out. Atmospheres will cancel out atmospheres over here in our in R. On this side, moles will cancel out moles. Kelvin will cancel out Kelvin. So our units do work out. The units cancel out, so the only unit left is going to be liters. And let me get rid of that. Okay, so all we need to do is solve for our volume. So we rearrange. All we have is, I'll write it here, volume is going to be 2.00 times 0.0821 liters is the only unit left there, times 373. And we need to divide by 1.5 atmospheres. Give our final answer. And let's see, this should be, I need to pull out a calculator. All right, let me pull up a calculator and just put this in. We've got 2 times 0.0821 times 373 divided by 1.5. And we get 40.8 liters. Should be the 3 sig figs. So 40.8 liters. So that should be in the right ballpark. One thing you do not have to memorize, but again, it's good to know for gasols, fairly common, comes into play, comes in handy sometimes, is at standard temperature and pressure, which is really 273 Kelvin, 1 atmosphere of pressure, 1 mole of any ideal gas occupies 22.4 liters. So I'll look at this problem. We've got 2 moles. That should be double that, 44 liters or so, 45 liters. A little bit higher temperature than 273, so maybe 50 liters or so. But there's also higher pressure. Higher pressure pushes the gases in, so at least 40 seems like it's in the right ballpark. So at least, again, that's why I call a sanity check. Make sure that your answer at least is reasonable. If I'd gotten like 3 liters or 800 liters, then I would know something's wrong there. So it's just a way to double check to try to catch any careless mistakes that we all can make. And so let's look at one more problem. At room temperature, the partial pressure of hydrogen and oxygen are measured to be 690. This is saying in a given sample of gas. 690 torr and 45 torr respectively. What's the partial pressure of the third gas in the mixture, water, if the total pressure is 770 torr? So here, obviously we're assuming that everything's constant, atmospheric, the total pressure is constant, volume is constant, temperature is constant. We have 3 gases mixed together, so the equation we need to use is just P1 equals P1 plus P2 plus P3 equals our total pressure. We only have 3 gases, so we just plug in and solve for the unknown. So really straightforward, but again, it's just looking at which equation do you use, which one makes sense. We can't use the other equations. We don't have a change in pressure, volume, or temperature. We don't have moles of any of these gases. We don't even have an actual temperature or pressure. Well, we don't have a temperature or volume to deal with. This problem is just assuming that the volume and temperature are both held constant. So P total is, of course, 770 torr. P1 is going to be 690 torr. P2, 45 torr. And we're solving for P3. So easy enough. Plug in and solve for P3. You'll get 697, 35. So it's going to be, what, 35 torr. 0.0 to proper sig fit. Actually, oh, sorry, it would not be 0.0. We're adding, subtracting, so it's precise only to the nearest torr. So it'll be 35 torr of water vapor, just to be more specific in my answer. And that's it. I like to double check. 35, 45 gives us 80 plus 690 gives us 770, so it's easy to double check careless math errors. And I will point out here, just to make sure, on exams and things, when you turn them in, box or circle, let me know what your answer is. Point this out now so you don't lose any points later on, because often people put numbers here and there everywhere, and I can't tell what your actual answer is. So just a good habit to circle for your sake and mine, what is your answer, what were you trying to get to. And also, this helps you at the end of your problem, make sure you're actually answering the question being asked. I've had quite a few students that miss 5 points on a 20-point problem or partial credit because they did everything correctly but didn't finish the problem. So look at this problem and say, well, our final answer is 35 torr. It's asking for the partial pressure of the third gas, so that's actually what's being asked for. Sometimes people don't do the last conversion step. The answer asks for maybe in atmospheres instead of torr, so your last step would have been to convert torr to atmospheres. So that'll be one step missing there. So just be careful. Again, it's just a good way to help you eliminate or minimize careless mistakes. So again, I hope this helps. There are lots of practice problems in the book. They're a good idea for you to work on. They help out in developing problem-solving skills, understanding the basic concepts, and will really help you in learning how to keep track of and deal with units.